Muted it.
Oh, okay. Okay, so is it good now? All right, so I guess I'll start from the beginning. So yeah, thank you to the organizers for the invitation. It's a great honor to be here, and I'm really happy to be in Toronto. So my talk will be more representation theoretic than any of the other ones. So I will be discussing finite dimensional representations of the queerly supergroup Qn. And this is joint work with Veras. So let me first define what the queerly supergroup is. So it's the second super analog of the Lie group GLN, and it's defined as the sub-supergroup of automorphisms of the standard rep CNN, which preserves an odd automorphism pi with the property pi squared equals -1. And it's easier to describe its coordinates in the Lie algebra setting. So the Lie algebra of Qn is denoted by mathfrak Qn, and it's the Lie sub-superalgebra of GLNN, which consists of endomorphisms supercommuting with pi. And in coordinates, if we choose pi to be this block matrix 0, 1, -1, 0, then Qn consists of block matrices A, B, B, A, where A and B are in GLN, and the even component is this block diagonal AA, and the odd component is the anti-block diagonal BB. So as Lie algebra, the even component is GLN. So now there's a few important superalgebras of Qn, which are analogous in the Lie algebra setting. So we have the Borel, which consists of block matrices of the form ABBA, where A and B are upper triangular. Then we have the nilpotent subsuperalgebra, where A and B are strictly upper triangular. And we have the Cartan subsuperalgebra, where A and B are both diagonal. Now, this final property about the Cartan requiring both of them to be diagonal, this is a special property for the queerly superalgebra. So in Katz's classification of simple Lie superalgebras, there's only one which has a Cartan subalgebra, which is not abelian, and this is Q. So the existence of an odd component in the algebra means that it's not abelian. And this is sort of the source of the really rich representation theory. So a lot of new representations appear. Okay, so the existence of this odd Cartan allows us to associate a non-degenerate Clifford algebra. So this Clifford supermodules will keep track of the H module. So for each weight lambda, which is in the dual of the even Cartan, we may associate a non-degenerate Clifford algebra by first making this symmetric pairing given by u comma v goes to lambda of supercommutator uv. So this is symmetric and bilinear, and then it has a kernel, so we mod out by the radical of this bilinear form, and we induce a non-degenerate Clifford algebra. I denote by Cliff lambda. And now it's a general theory that for any non-degenerate Clifford algebra, it's either a matrix algebra or it's a direct sum of matrix algebras. And in the first case, there are exactly two supermodules, which I denote by v lambda and pi v lambda. And in the second case, there's exactly one simple supermodule, which I denote by v lambda. And this pi is sort of it's denoted the parity change functor. So it's a functor, at least on the level of vector spaces, which just swaps the even and the odd grading. And then there's a natural induced action of the algebra. So now the theorem for classifying H modules is that these Clifford modules v lambda, well, you can induce it to an action over H0, where H0 acts by the weight and H1 acts by the Clifford algebra. And the statement is that this produces all possible finite dimensional irreducible H supermodules. And moreover, this category is semi-simple. So the Clifford algebra is semi-simple and the even component is semi-simple. And in fact, the whole H module category is semi-simple.
just to be in the loop. This V of lambda and pi V of lambda like while spinners, right? So a pair of
yes,
two spinner and well another two spinner.
Yeah.
So which together make Dirac spinner, roughly speaking.
Yeah. I'm not so familiar with the physics notation, but I do. Yes, these are spinor modules. Yeah. Okay. Now to go from H modules to G modules, it's the usual construction. So first we induce and then we take quotient. So there's this Verma module and lambda. So you induce from the Borel. So the V lambda is the Clifford module. You require the nilpotent to act trivially, and then you induce. And there's again a unique simple quotient denoted by L lambda. And there is a dominant integral weight lattice given by this condition. So for Q, the condition is that the weights are in non-decreasing order. So lambda I minus lambda I plus 1 is a non-negative integer. And in the case that they are equal, lambda I equals lambda j, then both of them have to be 0. And then in Katz's original paper, he showed that L lambda is finite dimensional if and only if lambda is dominant integral. So then the next story in the theory is to compute character formula for these L lambdas. So character formula here is, as usual, character means you keep track of the dimension of the weight spaces. And for generic and typical weights, so generic means lambda I is much bigger than the next one, and typical means lambda I plus lambda j is never 0. The formula looks like this. And this should remind you of the character formula, the Weil character formula for GLN. So it's sort of like a immediate super analog. And let me just make a couple comments. First, the highest weight space is not one-dimensional in the supersetting. It's equal to the dimension is equal to the dimension of this Clifford module, which is 2 to some power. And the next statement is all of these L lambdas have super dimension 0. So super dimension is the dimension of the odd minus the dimension of the even, and this is 0. And again, this is just immediate from the formula. And I only stated the character formula for generic and typical weights. And Penkov-Serganova actually prove it for all weights. And there's no closed form for the character formula. Rather, they give a recursive relation to compute the characters. And sort of the starting point of each of these recursions is going back to these generic and typical weights. Okay. So now I want to discuss this category of modules which we consider. So this is Qn, denoted by Qn mod. It consists of all finite dimensional modules over the supergroup Q, where morphisms are parity preserving. So the morphisms must send even to even and odd to odd. And I work in the algebraic setting. So the category G mod is equivalent to modules over this Harris-Chandra pair G0. And this means finite dimensional G supermodules where morphisms preserve the Z mod 2 grading, and G0 acts semi-simply. So let me explain. The first condition, morphisms preserve the Z mod 2 grading, is imposed so that the category is abelian, so that we can make use of cohomological tools. And the second condition, G0 acts semi-simply, well, you already know that SLN acts semi-simply, and now you're just imposing that the one-dimensional center also acts semi-simply. And this is just made to sort of have a handle over all the indecomposable objects. So in general, there's way too many indecomposables, but if you make this convenient assumption that G0 acts semi-simply, it's sort of easier to work with.
Sorry, I just had a quick question. Maybe I'm missing something. Where are you using capital G? Like, where are you using the Lie group structure? Like it says, you just have the Lie algebra, and nowhere is the Lie group mentioned. It says like supermodules with some conditions.
Yeah, so the supermodule, there's a categorical equivalence between modules over the supergroup Q and then modules over this Harris-Chandra pair G0. And sort of, I want to discuss modules, and to discuss modules over the group, I just discuss sort of these modules over the Lie algebra.
So you are inside the category of O.
No, I sort of a smaller category, only finite dimensional.
Okay, but
objects.
you are inside the category.
Inside, yes.
Okay.
Yeah.
Thank you.
So like Veras are not in my category.
What will be the difference if you consider just modules of your Lie superalgebra? So what is the group part, where group part plays role? That you're talking about a group, not just Lie superalgebra.
Well, I really want to work just in the algebraic setting. It's
Yeah, I understand. Just my question is very naive. So because when you speak about this pair, just Gothic G capital G0. So you consider a pair consisting of Lie superalgebra and the Lie algebra corresponding to the even part, right? And what's the difference with just simply considering Lie models of just Lie superalgebra, well, Gothic G?
yeah. So if
Where
so
there's condition that your representation integrates to representation of the group. So does it play a role?
It's the second assumption that G0 acts semi-simply. If you just consider modules over the superalgebra math frac G,
Yes.
and G0 does not act semi-simply, then there's too many indecomposable objects, and there's no real way to. Like,
Okay.
yeah, you're imposing a really strong condition by requiring the even component to act semi-simply.
That makes the G_0 X as well?
Yeah.
Okay, that's kind of the function both confusing.
Yeah, okay.
Thank you.
Yeah, okay, thanks. Now there's a Harris-Chandra homomorphism from the center to the ground field, and corresponding to this, we can give a block decomposition of the category Q and mod as a direct sum of these blocks. So Q and mod subscript chi means we consider modules whose central character is chi. Now, Sergeyev gave a condition for when two central characters are the same. It's this combinatorial condition. And in the case where all of the components of the weights lambda i's are distinct and the mu i's are distinct, this condition just reads that lambda and mu lie in the same SN orbit. So it's really sort of, it's not a surprising result.
And isn't this the typicality condition that you write there?
Yes, yes.
Okay, thank
yeah,
you.
it's exactly, yes.
Yeah, so it is more general and just say,
Yes.
you know, typical and then same orbit.
Yeah, so this condition just means that the weights have the same typicality. Yeah.
And sorry again for the question. So is there a simple description of the center of this Z of G?
Yes, there does exist.
So the theorem of Laplace apparatus, or whatever it's called. Yeah.
Yes, that's right. That's right. I will speak about that.
Okay. Okay.
Thank you. Yeah, the center is computed for all superalgebras. Yes. Okay. So Sergeyev gave a condition for when two central characters are the same, but sort of it wasn't until Vera in her ICM paper gave a really strong sort of classification of the blocks which actually appear. And it turns out there's only two types of blocks which appear in the category Q and mod, namely the standard block and the principal block. So the theorem states that if we have a dominant integral weight, then Q and mod lambda is block equivalent to Q and mod lambda twiddle, where lambda twiddle is either a standard weight. So for some QK where K is less or equal N, or it's this trivial weight, 0, 0, 0. So it's the block which contains the trivial rep and also the adjoint rep. And this integer K has a special name. It's called the atypicality of the weight. And sort of this notion of atypicality associated to weight appears many times in the literature. There's many conjectures about this weight, which I will not get into. And yeah, so the way Vera proved this theorem used heavily this notion of translation functor. So there's really only one functor one may define to go between blocks. So what you do is you have a module M, you tensor it with the standard representation so that you pick up weights of the form lambda plus epsilon I, and then you project onto the corresponding mu block. So that's the translation functor. And sort of, this is really the main tool used in this proof. Okay, so that sort of completes the classical theory about Q modules. Now I want to discuss sort of newer results. For this, I have to first set up some notation. So we have this notion of a superflag variety. If P is any parabolic in G, then we can define the flag supervariety G mod P. So it exists in the category of superschemes, and it also coincides with Manin's notion of flag superspaces, which he denotes by this symbol. And for any module over the parabolic P, we may geometrically induce it to a module over the group G by first constructing a vector bundle over G mod P and then taking global sections. And this functor is just left adjoint, and taking right derived functors, we have sort of a family gamma sub i's from P mod to G mod, where you map a P module to the ith sheaf cohomology of this induced bundle. Now, there's a way to define this geometric induction functor completely algebraically without worrying about the existence of G mod P. And this is due to Zuckerman. And I will just say on the gamma sub 0 component, so the functor, it's isomorphic to this functor take G0 finite vectors of the co-induced module V. And G0 finite means it spans a finite dimensional G module. The G0 orbit spans a finite dimensional G orbit. And another equivalent definition of this gamma sub 0 is, well, given below. Gamma sub 0 is just the maximal finite dimensional quotient of the algebraically induced module. Now, there's this typical lemma, which computes the result of inducing a Clifford module in the case where the weight is typical. And the result is that, well, the gamma sub i's are concentrated in degree 0. And in degree 0, you pick up just your irreducible highest weight module L lambda. And this is sort of an analog of the Bott-Borelve theory for superalgebras in the case of typical weights. It's a very ongoing research to do it for any weights, not just generic. And it's still open, and sort of currently the only progress is pretty partial, like only in the case where this V lambda is the trivial rep do we actually know the higher sheaf cohomologies in general. Okay, so now I want to define an Euler characteristic. So this Euler characteristic, it keeps track of the multiplicity of L mu and the gamma sub I. And we're living in the Grothendieck group of the module category. And in the case where we're working with the typical weights, well, sort of this gamma sub I only lives in degree 0. So then taking the character of the Euler characteristic, it only picks up the character of L lambda. So that's what I've written down here. So generically, the Euler characteristic, the character of it is equal to the character of L lambda. And
why capital C? So before the character is denoted by small c. It's different character.
It's the same character.
Same.
Yeah.
It's just super trace. Or super trace of what?
So the character here, it's keeping track of the dimension of each weight space. So formally it lives
So it's form of our series.
formal in the E, like, yes, form of our series.
In Q or whatever.
Yes.
And K is this pi in K, you got to bring what pi?
Yeah, so this means
So this pi in notation for the Grothendieck ring representation. So
yeah, so
stands
this is
for-
identifying L lambda with pi L lambda.
Okay, so
So in the Grothendieck group, we work
does
in
not distinguish this parity
Yes.
reversed models.
yes, sort of the only way we can make the result state nicely is if we work in this pi
Pi
preserving.
Pi
Yeah.
symmetrics.
Yeah.
Right. Thank you.
Okay, so the result is there's a virtual BGG reciprocity. So the Grothendieck group, there's a basis given by these L lambdas. So we can write down the E mu in terms of L lambdas with coefficients B. And then the statement is there exists coefficients A so that we may write the indecomposable projective object P lambda in terms of the E mu's. So this E mu plays a role of a virtual Verma module. Like in the ordinary category O of Lie algebras, there's this BGZ reciprocity. So this is what the statement is. And this coefficients A and B only differ by some small power of 2. And this small power of 2 is just sort of the only extra factor which appears for Q. In any other classical Lie superalgebra, this BGG reciprocity was proved by Gruson and Serganova. And sort of we just fixed this proof in order to account Q as well. And the next comment I want to make is, well, Vera computed all of these characters of L lambda. So we know what the coefficients B mu lambda are, because we also know what the character of E mu is. So knowing all the B's means we know all the A's by this relation. And so this allows us to compute the multiplicity of each simple in each projective. It's given by this formula. And once we know all these multiplicities, we know all the Homs between the projectives, and this gives us all the relations in the quivers, which I will now briefly explain. So recall there are 2 blocks which we consider, the standard and the principal. And in the case of the standard block, well, it turns out that the standard block is more or less equivalent to the principal block in 1 dimension lower because of this identity. And with this, we can now give a picture of the extension quiver for Q3 standard block. So extension quiver means all of these vertices are the simple objects, and an arrow between 2 vertices means there exists an extension. So there is an indecomposable length 2 module. And the previous slide computes all the extensions, and then BGG reciprocity computes all the relations. And immediately from this picture, we can give some nice results about the category. First, we can conclude the category is tame, and also it's not a highest weight category. And the next block is the principal block, and this is a lot more complicated. And again, here's the picture. So again, all the vertices are irreducibles. Arrows denote extensions in one direction, and then relations are given by here. And a corollary of this picture is the principal block is wild. In fact, it's the first example of a wild block for Q. And also, the category is not a highest weight category. Okay, and that is all. Thank you.